All right, welcome in everyone to this deep dive. We're going to be talking about something that might seem pretty theoretical, abstract algebra,
Yeah, it can seem a bit intimidating at first.
but I think especially for, those of you who are teaching high school math now or going to be soon, there's actually some really practical stuff in here.
Well, absolutely.
So we're looking at Gallian's book, Contemporary Abstract Algebra.
Yep.
And we're going to focus on 3 chapters. Chapter 4 is all about cyclic groups. Chapter 5 is permutation groups. And Chapter 6 is isomorphisms.
Right.
And the idea here is to kind of unpack those and think about how they might, actually be useful in the classroom, whether you're teaching geometry or discrete math or even some computer science principles.
Yeah, I think you'll be surprised how much these ideas connect to things you're already teaching.
Okay, so cyclic groups, what are those? So basically, it's a group that can be generated by a single element.
Right, so you've got this one special element, and it can sort of create the whole group.
Yeah, it's like a domino effect. You start with one element, and by repeatedly applying the group's operation, you can get to every other element in the group.
Exactly.
I mean, think about it. Elise Sosinski said that group theory achieved precisely that, a unity and indivisibility of the patterns underlying a wide range of seemingly unrelated disciplines.
Right.
I mean, it's pretty powerful. And cyclic groups are, sort of a key to understanding these patterns.
Yeah, they're like the fundamental building blocks.
Okay, so we've got the special element called a generator. So what is it about the generator that makes it so special?
Well, a generator has this unique property. If you repeatedly apply the group's operation to it, you'll eventually generate every single element in the group.
Okay, so let me see if I understand this. Let's say we've got the integers modulo 5 under addition. So that's 0, 1, 2, 3, and 4.
Right.
And we pick, let's say, 2 as our generator. If we add 2 to itself, we get 4. Add 2 again, and we get 6, which is 1 modulo 5.
Right, because we're always taking the remainder after dividing by 5.
Right, and then 1 plus 2 is 3, and 3 plus 2 is 5, which is 0 modulo 5. So we started with 2 and got to every other element.
Exactly. You see how that one element, too, generated the whole group.
Yeah, that's pretty cool.
It is.
Okay, so then there's this idea of the order of an element.
Right.
And this is different from the order of the group, right?
Yes, definitely. The order of an element is about how many times you need to apply the group's operation to that specific element before you get back to the identity.
Okay, so let's say we're looking at the group of integers modulo 6 under addition. So that's z sub 6 sub.
Okay.
We'll take 2 again. 2 plus 2 is 4, plus 2 again gives us 6, which is congruent to 0 modulo 6. So we had to add 2 to itself 3 times to get back to the identity, 0 away.
Right.
So that means the order of 2 in z sub 6 sub is 3.
Exactly.
Now, here's where I think this starts to connect to things that we might teach in high school. Cyclic groups have some really interesting properties that can help illustrate concepts that our students might be learning in other areas.
Absolutely.
So one of the big ones is that every cyclic group is abelian, right?
That's right.
Meaning that the order in which you perform the group's operation doesn't matter.
Yeah, it's commutative.
Which can be really helpful when you're trying to teach students about, order of operations and things like that.
Right. It gives them a clear example where the order doesn't matter.
Exactly. And then later on, when they start encountering non-commutative structures, they'll have that foundation.
Yeah, that's a great point. It helps them see the contrast.
And then there's this idea that any subgroup of a cyclic group is also cyclic.
Yes, that's an important one.
And that kind of demonstrates a hierarchical structure that might resonate with students when they're thinking about things like subsets or substructures in other areas of math.
Right, it's like a nested structure.
Okay, and maybe the most intuitive connection for high school students is this idea of periodicity.
Yeah, that's a big one.
In a cyclic group, you keep applying the same operation, and eventually you get back to where you started.
Right, you cycle back.
And that's like, rotations in geometry. Like, if you rotate a hexagon by 60 degrees 6 times, you end up back where you started.
Exactly. And you see periodicity in modular arithmetic, too, which is important in computer science.
Right. And even in trigonometry with periodic functions.
It's everywhere.
So it's this underlying idea of repeating structure that's so important. And cyclic groups really highlight that, which is relevant to a lot of different areas that we teach.
Absolutely. It reinforces those concepts of structural simplicity and patterns.
Okay, so before we move on, let's talk about some of the common misconceptions about cyclic groups.
Sure.
So one of the big ones is this idea that every element in a cyclic group is a generator.
Right. That's not true.
Just because an element belongs to a cyclic group doesn't mean it can generate the entire group. You have to actually check that.
Exactly. You have to make sure that if you repeatedly apply the operation to that element, you actually get all the other elements.
Okay, and Another common misconception is that all groups are cyclic.
All right, not every group has that nice property of being generated by a single element.
So it's important for students to understand that cyclic groups are just one type of group, and there are lots of other types out there.
Exactly, they're a special case.
All right, let's move on to chapter 5, which is all about permutation groups.
Okay.
So this might sound a little abstract, but it's basically about rearrangements.
Yeah, permutations are just ways of rearranging things.
And permutation groups are groups whose elements are permutations, and the group operation is the composition of those permutations.
Right, so you're combining rearrangements.
And I think this is a really important concept for teachers because it helps us understand symmetry and, just the idea of rearranging things in a systematic way.
Absolutely, it comes up all the time in different areas of math.
Okay, so let's start with the basics. A permutation is just a way of rearranging the elements in a set. So let's say we have the set 1, 2, 3.
Okay.
One permutation would be to move 1 to 2, 2 to 3, and 3 back to 1.
Right, we just shuffled them around.
And we can write that using cycle notation as 1, 2, 3.
Exactly. Cycle notation is a really handy way to represent permutations.
Yeah, it shows you exactly how the elements are being cycled around.
Another example would be 1, 4, 3, which means 1 goes to 4, 4 goes to 3, and 3 goes back to 1.
Okay, so that makes sense. And if an element doesn't appear in a cycle, it means it stays in its original position.
Right. We call those fixed points, and we usually omit them from the cycle notation to keep things concise.
Okay, so now let's talk about transpositions. A transposition is a special kind of permutation where you just swap two elements.
Right, it's the simplest kind of rearrangement you can do.
And it turns out that any permutation can be expressed as a product of transpositions.
That's right, no matter how complicated the permutation is, you can always break it down into a series of simple swaps.
And this leads to the idea of the parity of a permutation.
Right, parity tells you whether a permutation is even or odd.
So if you can express a permutation as a product of an even number of transpositions, it's an even permutation.
And if it takes an odd number of transpositions, it's an odd permutation.
And the parity of a permutation is always well defined, right? It's either even or odd, never both.
That's right, it's a fundamental property of permutations.
So like 1, 3, 2 can be expressed as 1, 2, 1, 3, which is two transpositions, so it's even.
And a single transposition like 1, 2 is obviously odd.
Okay, so now we can talk about the symmetric group, which is the group of all permutations on a set of n elements.
Right, we denote that as sub-sub.
And the order of the symmetric group is n factorial, right? Because there are n factorial ways to rearrange n elements.
Exactly.
And then there's the alternating group, which is a subgroup of the symmetric group.
Right, the alternating group, denoted as a sub-sub, is the group of all even permutations on n elements.
And its order is half the order of the symmetric group, so n factorial divided by 2.
Correct.
Okay, and one more important property of permutations is their order.
Right.
So the order of a permutation is the number of times you have to apply that permutation to get back to the identity.
Exactly. It's how many times you have to repeat the rearrangement before everything's back in its original place.
And if you write the permutation in disjoint cycle notation, the order is just the least common multiple of the lengths of the cycles.
Right. So if you have the permutation 1, 2, 3, 4, 5, its order would be the LCM of 2 and 3, which is 6.
Okay, so how does all of this connect to what we might be teaching in high school? Well, permutations come up all the time in combinatorics.
Right. Whenever you're counting arrangements or selections, you're essentially dealing with permutations.
And they also play a huge role in geometry when we're talking about symmetry.
Absolutely. The symmetries of a square, for example, can be represented as permutations of its vertices.
Right. So when we're teaching students about rotations and reflections, we're really talking about permutation groups.
Exactly.
And I think just understanding permutations in general helps students develop a more systematic approach to problem solving.
Yeah. It encourages them to think about rearrangements in a more organized way.
And Gallian even has this example of encryption using a permutation, which could be really interesting for students who are interested in computer science.
Right. It shows how these abstract ideas have real-world applications.
Okay, so our last stop on this deep dive is Chapter 6, which is all about isomorphisms.
All right. Isomorphisms. This is where things start to get really interesting.
So what is an isomorphism? Basically, it's a way of showing that two groups are structurally the same, even if they look different.
Exactly. It's like having a perfect dictionary that translates between two languages.
So you might have two groups with different elements and different operations, but if there's an isomorphism between them, it means they have the same underlying structure.
Right. They behave the same way algebraically.
So it's like they're twins, but maybe they're wearing different clothes.
I like that analogy.
So what makes an isomorphism an isomorphism? Well, it has to be a function that's one-to-one and onto.
Right, so every element in the first group has a unique partner in the second group, and vice versa.
And the key property is that it preserves the group operation.
Meaning that if you combine two elements in the first group and then map the result to the second group, it's the same as mapping the two elements first and then combining them in the second group.
So the structure stays intact.
Exactly.
And because of that, isomorphisms preserve a lot of important properties.
Right, like the identity element and inverses.
And the order of elements.
Exactly. If an element has a certain order in one group, its corresponding element in the other group will have the same order.
Okay, let's try to make this a little more concrete. So let's take the group of integers modulo n under addition, which is z sub sub.
Okay.
It turns out that this group is isomorphic to certain rotation groups.
Right.
Like, for example, z sub 4 sub is isomorphic to the group of rotational symmetries of a square.
That's right. You can map each element of z sub 4 sub to a rotation of the square, and the group operations will correspond perfectly.
So even though they look completely different, those two groups are structurally the same.
They have the same algebraic DNA.
And it's important to remember that just having the same number of elements isn't enough for two groups to be isomorphic.
Right. The way those elements combine has to be the same, too.
So like z sub 4 sub, which is cyclic, can't be isomorphic to a group that has 4 elements but isn't cyclic.
Exactly. Their structures are fundamentally different.
Okay, so what's the takeaway for teachers when it comes to isomorphisms?
Well, I think it really highlights the importance of understanding mathematical structure.
Absolutely.
It's not just about the specific elements and operations, it's about the underlying relationships between them.
And recognizing those relationships can help you simplify complex ideas.
Right, because you can relate them back to more familiar structures.
And it can also help you make connections between different areas of math.
Exactly. You start to see how things fit together in a bigger picture.
And there's this really cool theorem, Cayley's theorem, which says that every group is isomorphic to some permutation group.
Wow, that's amazing.
It is. It means that permutation groups are kind of like a universal language for groups. So understanding isomorphisms is key to understanding that.
Absolutely.
So I think the big message here is that even if you're not teaching abstract algebra directly, understanding cyclic groups, permutation groups, and isomorphisms can give you a much deeper understanding of math.
Yeah, it helps you see the connections and the patterns.
And it can make you a better teacher.
Absolutely.
So we encourage you to look for examples of these concepts in your own teaching.
You might be surprised at how often they come up.
And who knows, maybe you'll even get inspired to learn more about abstract algebra.
It's a fascinating subject.
Thanks for joining us on this deep dive.
Yeah, it's been fun.
We'll see you next time.
See you there.
Bye.